Hi, in this video, we're going to talk about the implementation of the quadratic probing hash table. Okay, now let's take a look at the code. So the first class we define is the bucket class, which holds the item that the client code wants to store in the hash table, as well as the associated state with the bucket. So the bucket can be in three different states. One is that it can be empty, meaning the bucket has never held anything in it. The second state is that the bucket is active, meaning it is holding a valid piece of data. So the third state is that it's deleted, which means that the bucket has at some point hold a valid item, but that item has since been deleted. And this is the done-the init method for the bucket class. It takes an item that we want to put in the bucket as an optional parameter. It can be none, right? So it will store that item. And if the item is none, meaning, well, there's nothing in the bucket yet. So in that case, the state of the bucket is empty. Otherwise, the state of the bucket is that active, that now we have something in the bucket. And next, let's define the actual hash table using quadratic probing, which is class hash QP, which is similar to what you've seen before. Let me point out a few things here. One is the max lambda. It really should be 0.5, right? We want to ensure that the load factor doesn't exceed half of the buckets. Now, we set it to 0.49. Now 0.5 just in case of rounding error, floating point numbers and that sort of thing. It probably should not, doesn't matter, but it doesn't hurt to set it to 0.4 now, 9. And then the done-the init method, nothing special here. We kind of, figure out the number of buckets. We set the lambda and then we allocate the space to store the buckets. So this is the buckets. And here we actually keep two pieces of information about the number of items that are in the hash table. So the number of items is really buckets that are active. And then we also keep a second number, the number of buckets that have been occupied. And this would track actually buckets that are either active or deleted. And we're actually going to be using the n number of occupied more often. Next, let's look at the hash function and the probing sequence. So the hash function, same as before, including the step where we have the modulo by the number of buckets. Now, the probing sequence, I wrote it as a generator. So you can tell by the use of yield keyword here. The reason is so that all the logic to generate the probing sequence would be encapsulated inside one generator. And as we'll see, this generator is actually reused by the different operations of the hash table, such as insertion and removal. This one, the iter index slow, works exactly how we describe it as using the probing formula, right? We just hash the key and we increment the hash value by the square of an increasing sequence, which the k goes from 1 to 2 to 3, so on and so forth, and then the k square would go from 1 to 4 to 9, the quadratic probing sequence. However, I did not end up using this generator because it is slower than this generator, which used exactly the same sequence as this generator, but this one is faster because this one only uses additions, whereas this one actually uses a multiplication. So the derivation of this is described in detail in the readings, again, if you have access to it. But it's entirely optional whether you understand how this works or not. Next, let's take a look at how to implement the insert operation. So given a new item, the overall job of the insert method is to find an available bucket into which we can place the new item. So in order to find that available bucket, we will use the generator that we just wrote, which would give us the index for the buckets in the order that we will probe by. For each of the bucket yielded by the generator, we will retrieve the bucket and take a look at the state that the bucket is in. If the bucket is an active bucket, but the item that's already in the bucket is equal to the item we're trying to insert, then we are trying to insert something that's already there, which is not allowed. So we raise a value error. Now, if the bucket is an empty bucket, then it is available and we can put a new item in that bucket. To do that, we set the state of the bucket to active. Now it holds an item, and we assign the new item to the item that is being held in the bucket. We increase the number of items in the hash table by 1, right? That's the number of active buckets. And we also increase the number of occupied buckets in the hash table by 1. That's the total of active and deleted buckets. So now that we have 1 fewer empty buckets, the lambda, or the load factor of the hash table, would have changed, and we would have to check to see if we have to rehash. So we will take a look at how rehash as needed is implemented in a moment. But after all of these are done, then we are done with the insertion operation. So we break out of the loop now. We don't have to keep going. Otherwise, we didn't find a duplicate. We haven't found an available bucket to insert a new item in. So in that case, we'll have to keep looping. Next, let's look at how rehash as needed is done. So we'll have to rehash when the number of occupied buckets, which was previously incremented here, when that exceeds our lambda, right? Another way to look at this is that we want to make sure at least half of the buckets are empty. So this will tell us that. Now, if that number of occupied buckets are too many, bigger than the max lambda, then we will have to do the rehash. And to rehash the buckets, we first keep a reference to the old buckets. And then we double the number of buckets we will have, but also find the next prime that is larger than that. We allocate all the new buckets, and then we go through all the old buckets, and for each one that used to be active, we take its item and insert it into the new buckets. And that concludes the implementation of insertion. Next, let's take a look at the Thunder contains method that, when given a key, will look up if that key exists in the hash table. So to do that, we go through the probing sequence again, right, based on what the key is. And for each of the index yielded by the probing sequence generator, we look at the bucket that it references. And if that bucket is an active bucket, and also the item in the bucket equals to the key, then we found the key that's in the hash table. And in that case, we say it's in the hash table, right? So we return true. Another condition is that we reach a bucket that is empty, and that, as we saw earlier, signals that we've reached the end of the probing sequence. So we don't have to look for any further, and that means the key that we're looking for is not in the hash table. So let's look at one more operation, and that is to remove a given key. By now we know the drill. We'll go through the sequence, the probing sequence yielded by our sequence generator that is based on a key. And for the bucket that it references, we check the state if the bucket is active, and if the item in the bucket equals to our key, then we found the bucket that contains the key. And what we can do in that case is we set the state to deleted, right? So it used to be active, but now it's transitioned to a deleted state. And therefore, the number of items, which keep track of the number of active items in the hash table, that is decremented by 1. If, on the other hand, the bucket that we run into is an empty bucket, then we can terminate our probing sequence because we just did not find the key. Now that we've completed the three methods, insert, then the contains, and remove, we can do a fair amount of testing. And remember, we actually wrote a lot of tests in our last implementation of the hash table using the separate chaining, and those were actually generic tests that uses the same public method, like insert, then the contains, and remove, and it does not assume anything about how the hash table internally handles the collisions. So we can actually reuse all of those tests to test our new hash table QP class. And we can do that easily by importing the hash table test cases, create a new hash QP test case that inherits from the hash table test case, and simply overriding the hash table type. Now it is our hash QP class. And now I can run the full suite of tests that we wrote earlier. I'm not going to finish running them here. They are going to take a while. But rest assured that the hash QP class does pass all the tests. One more thing that I'd like to mention is that inheriting the test case this way, it's easy to run every test that was in the hash table test case. But if we want to just run one individual test, say for example test remove 1, it takes a little more work, but what we can do is simply to define the same test, and just in this test simply call the super version of that same test, and that way we can just run one of the tests. And this concludes the video on the HashQP implementation.